Hello everyone, this is Mingqi Han and this is the video explanation for homework 11, question 1. So in this question, we are given that xt is a WSS wide sense stationary with autocorrelation RXX tau, and its power spectral density is SXX of omega. So the part A wants us to prove that its autocorrelation is real and even. So for the first part, to prove it's real, simply write down the autocorrelation in its expected value form, and it's looking like this. And the middle part here would be over here. So, and this is same thing as this. And we know that xt plus tau and xt are both real value, and their multiplication should be a real value, and their expected value should be a real value. So its autocorrelation is real. And the second part, we wanted to show that RXX is even function. To prove that, it's simply just to prove that RXX tau is the same thing as RXX minus tau, and we write it in its expected value format, and just like this. And when we swapped the the order inside its expected value, so xt plus tau times xt is swapped as xt times xt plus tau. In this case, we're essentially getting a minus tau, and yeah, so this is what it looks like. And so that we have the minus tau of RXX is the same thing as the tau of RXX. So we know that RXX is even. And for the second part, we are to find out that its power spectral density is an even function, and we also want to know that it's non-negative. So to prove that it's a even function, we know that the autocorrelation and its power spectral density is essentially a Fourier transform pair. So what we do is we apply Fourier transform to the autocorrelation. We get to this part by solving this, and by removing this j and sine omega and changing that to cosine omega, we have this function, which I negated one step, which is the same thing but without a minus sign. So for a cosine function, well, cosine function well, is symmetric with x equal to 0. So minus omega tau inside the cosine function is the same thing as the omega tau of the cosine function. So that minus well, the minus omega sxx is the same thing as the omega of sxx. So we proved that. We know that it is an even function. And for the next part, well, we are to prove that it's non-negative. So we suppose that there is a LTI system, which is let's say it's a really good bandpass system. It's an ideal one with the passing band is equal to 1, and everywhere else is equal to 0, which is undoubtedly a LTI system, and there's no distortion because it's ideal. And here we have the well, how the bandpass filter or system, how it behaves. So what we need to do is what we do next is to use the expected value of yt squared, calculate that with the bandpass system inside here, because we already have xt. we want to figure out the expected value of yt squared, and we solve this function. And by doing so, we simply proved that, well, here's positive infinity, here's negative infinity, but everywhere is assumed to be 0, and only between w1 and w2 is equal to 1 is equal to the original function. So because this is LTI system, the input is xt, so the only thing that's passing is not between positive infinity and negative infinity, but between w2 and w1, and w2 is strictly larger than w1, so that's no problem. By solving that, we have that for this part is always larger than or equal to 0. So therefore, we proved that it is a non-negative function. And that's everything for this question.